Hi, my name is Olivia Sablan, and I will be presenting my integrated lab research on renewable surfactants. I'd like to start by giving some background on green chemistry, the field that this project is in. Green chemistry has experienced much growth because it addresses important environmental concerns such as depletion of resources, climate change, toxic waste, and pollution. Chemists approach these issues by working to decrease the severity of reaction conditions, meaning decrease the pressure, temperature, etc. the reaction must be conducted at, minimize hazardous waste and materials, and increase efficiency of reactions. By proposing new methods, engineering new technologies, and creating new materials, the environment can be better protected. The goal of green chemistry is to create more sustainable and ecologically friendly chemical practices. Synthesizing a new, renewable, non-toxic surfactant is the purpose of this study, which aligns with the goals of green chemistry. Herbicides have become a recent concern because of the potential to cause cancer in humans. They are widely used to eliminate weeds by preventing protein synthesis. The chemical makeup of most herbicides, like Roundup, is hard to determine because patents protect companies from making this information readily available. For this reason, it is difficult to establish what makes the formula so toxic. The active ingredient in most herbicides is glyphosate. However, glyphosate was proven to be non-carcinogenic. Studies have now shown that the surfactant is what is making the herbicide so toxic. Surfactants are used to help spread the herbicide onto the surface of plants. They are composed of hydrophilic and hydrophobic groups, which allow unique chemistry to occur. Hydrophilic means water is attracted, and hydrophobic means water is repelled. In the case of renewable surfactants, the hydrophilic group is the polar head synthesized from carbohydrates, and the hydrophobic group is the nonpolar tail synthesized from fatty acids. Because of these properties, the fatty acid tail works to decrease the surface tension, while the polar head group allows the surfactant to remain soluble. This increases the effectiveness of the dispersal of the herbicide. This project aims to synthesize a renewable, non-toxic surfactant. This surfactant would have renewable properties because it is synthesized from carbohydrates and fatty acids, which are naturally occurring and easy to obtain. Various sugars were attempted to convert to a surfactant, including D-xylose and D-galactose. To begin making the surfactant, the polar head group was first to be synthesized. This is referred to as the C-glycoside ketone. The two monosaccharides used in this experiment include D-xylose and D-galactose. The top scheme is xylose here, and the bottom is galactose. The anomeric hydroxyl group is represented by the wavy line here. This means that the sugar is converting back and forth from one anomer to the other, with the hydroxyl group rotating up and down. The anomeric hydroxyl group in each sugar was replaced by a ketone in this synthesis to form the C-glycoside ketone. The solvent for the C-glycoside ketone varied in this study. Acetylacetone and acetone share similar properties, and it was predicted they would have the same success in this reaction. Both solvents were used in the synthesis step in scheme 1 and 2 for both D-xylose and D-galactose to investigate the efficacy of each solvent. The experiments with acetone as a solvent formed a homogeneous solution mixture for both D-xylose and D-galactose, meaning the solution was one consistency. The reaction mixture was transparent and yellow for both of these. It consistently stayed homogeneous as the reaction progressed and was vortexed. The reactions with acetylacetone formed a non-homogeneous solution mixture for both monosaccharides, meaning the solution had layers. The top layer was transparent and clear. The bottom layer was transparent and yellow. The yellow was a similar shade to the acetone experiments. Both of these reactions were frequently vortexed because of the non-homogeneity, but remained separated for the duration of the experiment. The top layer in these reactions became more opaque, cloudy, and white as the reaction progressed. After evaporating the solvent off of the reaction mixtures, the product that formed was an orange and white solid for all reactions. In other studies, the C-glycoside ketone was a yellow oil. The phase of the product could give evidence that the reactions did not succeed. Since spectral analysis was not available during this study, success of each reaction can be interpreted from qualitative data. The difference in solution consistency between the acetylacetone and acetone experiments may suggest the intended product may not have been synthesized in both cases. Although each product had similar properties after drying, the solution properties may indicate that only one solvent can work successfully in this reaction. This will be confirmed when spectra are gathered. In the future, the fatty acid tail must be synthesized. Then it can replace the ketone in the C-glycoside ketone. And the polar head group and nonpolar tail group will be attached. Once attached, the final surfactant must be characterized to see how effective it is in comparison to the commercial surfactant used in broad-based herbicides like Roundup. Qualitative evidence showed that different solvents in the C-glycoside synthesis may change the success of the reaction. Spectra must be gathered to make clear conclusions regarding the efficacy of the solvents. In the future, the fatty acid tail will be synthesized to replace the ketone group. If these synthesized surfactants prove to be effective, then they can begin to be used in place of current and toxic surfactants. Thank you so much for taking the time to listen to my surf presentation. I really appreciate it.